So far we have done this. So this is the point pk minus 1, xk minus 1 comma yk minus 1, and here is the point pk, namely xk yk, and I want to approximate the length of this arc pk minus 1 pk, which is approximately equal to this length. But this length I can measure using Pythagoras theorem. It is square root of this length plus square plus this length square. This is delta x, this is delta y. Delta x is xk minus 1. Delta y is yk minus 1. So I have substituted for delta y as yk minus 1. Now, initially I assumed that my function was continuous. Let me assume my function is differentiable. So assume f is differentiable. Okay, then I can use mean value theorem. So what is mean value theorem? F of b minus f of a equal to b minus a into f dash c for some c in between a and b. So let me apply mean value theorem in the subinterval yk minus 1 comma yk. Xk minus 1 comma xk. So this is my mean value theorem. So apply mean value theorem in xk minus 1 xk. We get there exists a ck in between xk minus 1 and xk such that f of xk minus f of xk minus 1 is equal to xk minus xk minus 1. It is delta x into f dash of ck, where ck is a point in between xk minus 1 and xk. Now substitute for yk minus 1 here. This is precisely yk minus 1. So yk minus 1 is delta x f dash of ck. Call this as 1, substitute in 1. What I will get? Length of pk minus 1 pk arc is equal to square root of delta x the whole square plus square of this. So what is that? Delta x into f dash of ck whole square. So let me take delta x whole square out. So from the square root, if you take it out, it will be delta x into square root of 1 plus f dash of ck square. This is the length of this typical kth subarc vk minus 1 pk. Now what is the length of the whole curve? It is the length of the subarcs, sum of the length of the subarcs. Therefore, length of curve is equal to length of curve equal to sigma sum of the length of the subarcs. So it is sigma is equal to, or k equal to 1 to n square root of 1 plus f dash of ck whole square delta x. But the thing is, length of pk minus 1 pk, it is not exactly this, it is actually approximately equal to, this was actually hypotenuse of that triangle. Our arc is different from that hypotenuse. So this length is approximately equal to. Therefore, the whole length of the curve is not therefore exactly equal to, it is actually approximately equal to. Now I want to find out the actual length of the curve. So what I will do, I will refine my partition. I will add more and more points to the subinterval AB equally spaced and take the limiting case. So length of the curve is therefore approximately equal to length of curve exactly equal to limit n tending to infinity sigma k is equal to 1 to n square root of 1 plus f dash of ck whole square delta x. That means xk minus 1. What is this? This is precisely integral a to b square root of 1 plus f dash of x whole square dx by the definition of the definite integrity. So this is our formula for length of the curve. Length L is equal to integral a to b square root of 1 plus f dash of x whole square dx. I will make a remark. With that, we can start solving one or two problems. So, remark, if x equal to g of y is differentiable with a continuous derivative, here also in this case f is differentiable with a continuous derivative f dash, that is also assumed. I think I forgot to mention it. So is differentiable with a continuous derivative here y is varying in between c and d. So x is expressed as a function of y. Then length of the curve is equal to integral c to d square root of 1 plus g dash y the whole square dy. This is the formula for length. So one is y as a function of x, in case this is the formula for length, and the second case is if x is written as a function of y, then this is the formula for length. Off ചെയ്തു വന്നു.